Hey, what's up, guys? So welcome to my Galois theory second videos. So previously, in a previous video, I introduced the field extension. So in order to understand, I should say the algebraic field, the algebraic extension, and in order and the finite extension. So in order to understand the Galois theory, we need two definitions. One is the separable extension, and the one is the so-called normal extension. Okay, so basically, the Galois theory need to have the three conditions, which is a finite, separable, and a normal extension. So combine three of them. Usually, these two, if an extension has these two, this is defined to be Galois extension. Okay, so Galois extension need to introduce the separable extension, normal extension, these two conditions. So let me just introduce the separable extension. So separable extension is a simple idea, very, very simple. So recall that suppose I have a polynomial in variable x, as one can write as this. And one can do the derivative. Okay, so this is the derivative. Okay, so theorem what? So theorem says that if A belongs to K and P of X belongs to K of X, then the following are equivalent. Very, very simple abbreviation. Okay, the first one is that A has, A is a multiple roots. A is a multiple roots of P of X. The second is that P of A is 0 and P prime of A is 0. Okay. So basically what I'm saying is that if A is a multiple roots, then it's the derivative and it must be all 0. Okay. Hopefully this is very obvious. Okay, so let's quickly do the proof. Proof. Okay, so let's say I have 1, and which is A is multiple roots, so I can say P of X is X minus A to the K Q of X, and K greater or equal to 2. Now I do the derivative. Right, so I get this. Now I can plug, since K greater or equal to 2, right? So this is greater or equal to 1. So I can plug P of prime of A 0. Okay. Now, conversely, now suppose 2 is correct. So if P of A and the P of prime A is 0. Okay, so P of A is 0, right? P of A is 0. That means I can write P of X equals to X minus A times Q. Then the P prime of X will be what? Will be what? P prime of X will be Q of X plus X minus A Q prime of X. Okay, and I know that P prime of A is 0, so which tell me that Q of A is 0. So I mean I can also write Q of X equals to X minus A times S of X. Okay, I plug it in, I get P of X equals to X minus A squared S of X. So A is a multiple roots of P. Okay. Now this is the important theorem. No, sorry, definition. So now we can write a definition of the separable. So separable means no multiple roots. So that means if you have a K is a field extension over K, F is a field extension over K, is a separable when the following holds. So the first condition is that this extension is algebraic. Okay, and the second is that so basically given L belongs to as you say use L. Okay, given for all L belongs to L, the minimum polynomial. So minimum polynomial P of X of L has no multiple roots. Okay. So separable means that all the minimum polynomial of given L has no multiple roots and the algebraic extension. Okay, so and this is in Galois theory. Usually this is almost trivial since we have the following theorem. So theorem, if let's consider that I think this is let's consider this is algebraic extension. If the characteristic K is 0, then the second condition holds. Okay, so basically if your field is the rational number or the real number, complex number, such that the characteristic is 0, then the P of X has no multiple roots. The minimum polynomial always have multiple roots. Okay, the reason. So let's go to a proof. Actually, this is trivial, right? The reason is that if the characteristic K is 0, that means the degree of P prime is always degree of P minus 1, right? Because this n x minus 1 will not be 0 because an is non-zero, right? If the characteristic K is related to n, then it may be 0. So degree P prime, degree P minus 1, right? So that means P must have no multiple roots. Otherwise, one can use P prime as minimum polynomial. Okay, so if I say that degree of P has multiple roots, then the degree of P prime, then P prime can also serve as minimum polynomial, but the degree of P prime has the non-zero, is not a 0. Okay, and this violates the minimality. So basically, then one can say that if characteristic K is 0, then the algebraic extension will give you the separable extension. So if character K is 0, then algebraic extension will give you the separable extension. So separable is not the important case that we need to worry about. The difficulty in the Galois theory is so-called a normal extension. Okay, so let's go to the final theorem. This theorem is also, I should say, important one. So let's consider that we have this field extension and L over K is algebraic, and also L over K is separable. Then L over M is separable. So why? The reason, so proof, trivial. Okay, the reason is that now if you take L belongs to L, right, then there's a minimum polynomial P. So P of X has no multiple roots in L, right? P of X no multiple roots in L, right? But the M is a subfield, right? So P of X has no multiple roots in L, the same as in M, right? Because now P of X may have more factor, can factor through in some case in M, right? Okay, so maybe I should say this. Probably this is not a good way. So let's say this. So given L belongs to L, right? There is a minimum polynomial P of X in K of X, such that the P of L is 0, right? Okay, now you can in M, right? in M there may be another minimum polynomial. So there exists a Q of X belongs to M of X, such that the Q of L equals 0. And then by the previous theorem in the previous video that I proved, Q of X divides P of X. So if P of X has no multiple roots in L, then Q of X will not have multiple roots in L. So if P of X is simple, so simple means that no multiple roots, then its factor is also simple, right? So Q of X is simple. Okay, that's it, right? So now in the Galois extension, if we assume that this is separable, then the L quotient n is separable. Okay, so next time we will talking about another technical property called normal extension. Once we have the normal extension, then we can finish the Galois. We can start to prove the Galois theorem.